Hello, and welcome to our final lecture in our GI module. I meant to get this posted earlier this week, but hopefully tonight's not too late, so we'll go ahead and dive right in, talk all about the physiology of the liver and what happens when the physiology starts to malfunction, get some dysfunction going on. So with that said, let's go ahead and go over our basic objectives. Of course, we want to look at the basic anatomy of the liver, some basic functions, blood flow, structures, and the histology. We'll talk about how bile is being made and how it's excreted, along with bilirubin and the other substances that we would find in the bile. We'll also talk about some of the liver's other functions and metabolic pathways as well, and we'll also look at some jaundice, some liver liver function tests, as well as a few different diseases. So the first thing we want to think about with the liver is its major role in splenic circulation, how it has a central kind of a guardianship role, if you would, protecting the body from all of the blood that's coming in from our GI tract. So imagine for a moment we have our celiac artery here that of course is sending blood to your liver, to your spleen, and to your stomach. Then we have the superior mesenteric artery, which is supplying our pancreas, our small intestine, and then the inferior mesenteric artery, which is supplying the colon. All of this blood then from these major organs, from the spleen, the stomach, pancreas, small intestine, colon, they will all travel back to that liver, or to that liver rather, and the liver processes and monitors this blood before sending it and releasing it into general circulation through that inferior vena cava. So in this way, it has this what we call a first pass position to where all the blood flow goes through the liver first before the rest entering into the rest of the body. And this diagram just kind of shows the same illustration, showing us our liver here in that hepatic portal circuit. One thing I do want to mention while we're thinking about the blood flow coming into the liver through the splenic circulation, you'll notice most of the blood flow is actually directed to the mucosal layer, about 75% here going to that inner layer, and then with another 25% going to the muscularis layer towards the outside. You'll also notice if we take a look at a villus within the intestinal epithelium, or the intestinal mucosa rather, that there's a steep pressure gradient as we get towards the tip. So there's a decent blood supply down here, decent oxygen supply. But as you get towards the tip, it becomes more and more, or the pressure becomes less. And that's important because the villi really receive low blood supply anyway and the low oxygen. And so anything that would disrupt this, any type of perhaps a constant vasoconstriction that reduces this blood flow, can make this tissue ischemic. And if it becomes ischemic, that can affect the tight junctions between these cells, allowing the bacteria to infiltrate into your small intestine. Excuse me. Now, like I mentioned, the liver is the guardian to the body. It's going to have that first pass where all the blood is coming in from the visceral organs here before entering into the rest of the body. And we'll take a look at its role here in a little bit. But in the meantime, let's take a look at some of the major functions of the liver. And of course, the liver does a lot of different things. For one, it filters and removes your old red blood cells and any other foreign substances. This can be done physically through the Kupffer cells rather. And these Kupffer cells, they are very prominent in the liver, making up about 80 to 90% of all fixed macrophages of the reticuloendothelial system present here. They're in the liver. Of course, the liver is also going to play a role in activating different vitamins. If you guys remember, we talked about the activation of vitamin D. Liver had a role in that. And later on, when we get to the endocrine system, we'll see how the liver plays a role in activating your T4 hormone as well. In terms of digestion, the liver's main role is to synthesize and secrete bile. And it's also going to have a role in metabolizing carbohydrates, proteins, and fats. In addition, it's going to play a major role in detoxifying, going to detoxify both endogenous substances, things that our body makes like steroids and hormones, as well as exogenous substances as well, drugs, toxins, and so forth. Of course, the liver is also going to be a major role in storing iron and storing different water-soluble vitamins like vitamin A and vitamin B12. And we'll also see its role in plasma protein synthesis. Most plasma proteins are synthesized by the liver. There's a few exceptions like the gamma globulins, but the alpha, the betas, albumin, fibrinogen, most of your clotting factors, all of these are synthesized right in the liver. And of course, your non-essential amino acids, a lot of your non-essential amino acids can also be synthesized in the liver. So we can see right away, hopefully you guys are familiar with a few of these roles, but the liver is doing quite a bit. Excuse me. Now, what we want to look at to understand how the liver functions are the different functional units. And for right now, we're going to stick with this little guy here. This is called the hepatic lobule. And this hepatic lobule is what we like to think of as one of the functional units of the liver. But it's not the only one. I'll get to that in a second. First, I should preface that the liver, of course, is the largest internal organ. And you're going to see that it makes up 2 to 5% of the body weight. So a pretty good chunk of that body weight goes right to that liver. Now, like I mentioned, the functional unit is the hepatic lobule. And in the liver, we have about 50 to 100,000 of these. Now, to understand the organization of this, what we like to think of as a classic lobule, we can see in the middle we have this central vein. And around the central vein, we have these plates or these rows of hepatocytes. Now, at the lateral edges, the distal edges here, we have these groups of 3, these what we call portal triads. And each portal triad has, of course, our bile duct, so a branch of the bile duct is bile ductule, a branch of the hepatic portal vein, along with a branch of the hepatic artery. And so this would be the basic design of a hepatic lobule. Now, these hepatocytes that line the lobule, that makes these plates, they will make up about 80% of the parenchymal volume, so they make up a good chunk. And they form this barrier, if you would, between 2 separate compartments. And these separate compartments are quite different in their composition. First of all, we're going to see these little tiny bile canals, which we'll call the bile canaliculi. You'll notice that each bile canaculus is formed from where the 2 cells join together. So these cells are actually held tightly together, and then there's just a little bit of an opening to where we have that lumen here for that bile canaculus. You'll also notice in between the hepatocytes these big discontinuous capillaries, these sinusoids. These sinusoids are fenestrated, so they're very porous. They're going to allow large solutes, amino acids, even entire proteins to move into and out of the capillary spaces. In addition, around the capillaries, there is an extra space between the hepatocytes and the capillary endothelium. This is called the space of Dease. So here you can, for example, you can see a space of Dease or Dease if you'd like, that surrounds this capillary bed here, supplying a little bit of a space between it and the hepatocytes. Now, this will play a major role in the removing excess fluid and other substances from the blood. And you're going to see a lot of this will be going out through the lymphatics as it's cleared away from the liver. Now here we have a couple of hepatocytes joined together, and you'll notice that they have 2 different faces or 2 different membranes. The first one we'll look at is the apical surface. The apical surface is referring to this surface here where the 2 hepatocytes are joined together. So this would be an apical surface, and this would be an apical surface. The basolateral surface, this is the basolateral surface here that's actually facing this space of Dease. So here we can see our sinusoid, and it has those large spaces that's fenestrated. And then in between the sinusoid and the hepatocytes, here is that little space of Dease here. Now you'll notice on the basolateral surface, we do have these microvilli. These microvilli do project downwards into this space of Dease, increasing the surface area of the hepatocytes. Now, when we look at the tight junctions that between the 2 hepatocytes, these are what we like to think of as an intermediate tightness, which means they do allow little things to go through, but they do have a pretty good tight barrier to prevent most things from crossing. Gap junctions. Gap junctions are connecting the cells together. So here we can see a gap junction between these two hepatocytes. And that's going to allow for the diffusion of small electrolytes and small molecules in between the two cells. As we can see here, there are other cells involved in the hepatic lobule. For example, we have endothelial cells. These are the cells that line the sinusoid walls. So here we have some few endothelial cells. And they are going to be fenestrated, and that means they're going to allow solutes through, but not large things like cells into that space of Dease. Of course, we can't forget about our good friends, the Kupffer cells, or the Kupffer cells rather, these large stationary macrophages that are fixed in place that make up that big 80 to 90% of the reticuloendothelial system, the RES, or the rest system. So these guys can physically remove any debris, bacteria, parasites that might enter into the sinusoids. Of course, we don't want to forget about our stellate cells. And here's a stellate cell, and you can see inside these little tiny lipid droplets. And that's because it's having this role in the storage of vitamin A. Now, one thing you will notice is that these guys do become activated with injury. Things like cirrhosis, for example, make these guys become activated, and they will start to lay down a layer of collagen, and this is going to result in fibrogenesis of the liver. Now, when we look at the blood supply to the liver, you'll see there's two primary sources. 25% is coming from the hepatic artery, so hepatic artery right here bringing in 25%, while most of the blood is actually coming from the hepatic portal vein. 75%. That's pretty darn rich. Now, it's important to stress that the difference between the two is vast, or is important. The hepatic artery is bringing oxygen-rich blood, so this is nourishing the cells here. So, for example, as the blood is coming up through this hepatic artery, these cells that are sitting right next to it, they're going to have a good blood supply because that's where the oxygenated blood comes right through. Now, the hepatic portal vein, on the other hand, this is bringing in nutrient-rich blood, but it's oxygen poor. So these cells, for example, over here that are sitting next to this hepatic portal vein, they will actually get a poor blood supply, relatively speaking. Not poor blood supply, but a poor oxygen supply, because this blood supply is nutrient-rich, but it's oxygen poor. Now, you will get some mixing. We'll talk about this mixing, but we can see from the right hepatic artery, you get some blood that flows across into the bile system, and then some of this fluid can come back here and be reabsorbed and reprocessed by the hepatocytes. You will notice that these three vessels, the hepatic artery, the hepatic portal vein, and the bile duct do travel in a linear fashion here all together, and we call this a portal tract. Now, I know it's weird because we called these things triads earlier because we have hepatic portal vein, hepatic artery, and bile duct. That's three. But don't forget there's also lymphatic and nerves involved that travel along with these. So there's really a few more things to add to this pathway. Here's the what we call the peribiliary plexus I was mentioning, where you get this mixing of blood between the right hepatic artery here and the bile duct over here as it kind of goes back and forth. And this is going to provide a bidirectional exchange, if you would, of different solutes from the bile duct, and it allows them to adjust and to monitor the solutes as they're cycling back to the hepatocytes. Now, as we look at the bile ductules and we start to go further out away from the hepatocytes, you will notice there we go. These special groups of cells called cholangiocytes. Now, these cholangiocytes, these are lining the bile ductules. These guys right here. And in their position, they are especially designed to modify the composition of bile. Right? So as the bile is being produced from the hepatocytes, it's going to be secreted through these little tiny bile canaliculi, eventually into these terminal bile ducts, and then into this perilobular bile duct, and then into the interlobular bile duct. As it goes through, then these coagulocytes can reabsorb different solutes, glucose, amino acids, and things like that. Couple things to note about the blood flow going through the liver. You'll notice that it has a high blood flow and it's under very low pressure. There's very low vascular resistance. So, for example, we can see that the sinusoids receive about 27% of your total cardiac output. That's quite a bit. Notice once again we have about that 75 to 25% split. About 1050 is coming from the hepatic portal vein, whereas only 300 is coming from the hepatic artery. So once again, vast majority of blood is coming from that hepatic portal vein, but it is worth noting it is oxygen poor blood. Of course, there's also low vascular resistance as you go through the liver. If you look at the portal pressure in a portal vein, it's only 9 millimeters of mercury. That's very low pressure. Notice in the hepatic vein, it's 0, so pretty much close to 0. The point is the difference between these two, the 9 and the 0, is so small that we have very low resistance here to the blood flow through the sinusoids. All right. Now, another important thing to consider with the liver is its role in lymph formation. About half of the lymph that's formed in the body actually arises from the liver. So the liver has a pretty big, important role in this formation of our lymph. And you'll also notice, like I mentioned earlier, the sinusoids are very permeable. They have a lot of fenestrae. And in addition, there are spaces of Dease where the cells are discontinuous, allowing for large substances like proteins into and out of the sinusoids. Excuse me. Now, one of the things about the liver is that you can't break it down into functional units like you can the kidney with the nephron. The liver is a little more complex because there's not one section that can do all the jobs of the whole liver. So what we've done here is actually devised a few different types of functional units that each carry out their own function. So for example, this right here, this is what we think of as the classic hepatic lobule. We have our central vein in the middle, and we can see blood flow coming along from the portal vein here, and not that way. Let me erase that. And from the hepatic artery. Boop. There we go. That's better. So these guys are both coming in here like this. All right. And so that's how we're organizing this, is this drainage of blood from the portal vein and the hepatic artery that's going kind of inwards towards that central vein. But that's not the only way we can describe a lobule. Another way is to look at a triad out here. And we're looking at basically the portal triad that's all being drained by a single bile ductule. So let's suppose we focus on this guy right here. Well, if this is the case, well, it's going to receive bile from this lobule, and this one as well. So because of that, we're going to look at this this portal lobule as being the one that's where all the hepatocytes are drained by a single bile ductule, if you would. Now, a third way to look at the functional units is what we call the portal acinus. And this is emphasizing the oxygen gradient between the branch of the hepatic artery and the central vein. So you have to think, as blood flow is leaving, as it's going through these hepatocytes, the oxygen gradient is going to decrease more and more. So these guys out here, we'll say this is zone 1, they have the most oxygen because they're sitting literally right next to these branches from the hepatic artery. So this is what we like to think of as zone 1. Highly oxygenated, just came in, and is nice and fresh. But then as the blood flows inwards, it will become less and less oxygenated, just like that. Now, because of this arrangement where we have different zones, if you would, depending on their proximity to these branches of the hepatic arteries, each zone has different roles, different functions, if you would. So, for example, in zone 1, this is going to have the best circulation, and these cells are also the first to regenerate. Right? Zones 2 and 3, as you start to move further and further away, these are already perfused by the hepatocytes in zone 1. So they're not going to be regenerating as much, if you would, as you would see in zone 1. Oh, there we go. Now, chemically speaking, or metabolically speaking, we see different reactions going on in different zones. So, for example, zone 1, that's most oxygenated, this is carrying out oxidative energy metabolism. It's breaking down energy for metabolism. Also, you'll see most amino acid metabolism going on here as well. You'll also see the formation of urea. We'll talk about urea with the urea cycle, and gluconeogenesis and cholesterol synthesis as well. So there's really a lot going on in zone 1. As we move out to zone 3, and you get further and further away, you'll notice the activity in the cell changes. These cells out here in zone 3, they're more important for glycogen synthesis, the storage of glucose for in-between meals. It's also important for glycolysis, breaking down the glucose for energy, and lipneogenesis as well, making lipids from non-lipids. So we'll get to that later on. So we can see that these different zones do indeed carry out different types of reactions. Now, with that said, let's take a look for a moment at bile formation. Couple things to keep in mind. You do make anywhere between 500 to 1,000 liters or milliliters of bile every day. And it's being secreted in 2 distinct phases. The first phase involves the hepatocytes themselves. These guys secrete bile that's rich in acids, cholesterol, and other organic constituents. But once that gets released into the ductal system, the ductal epithelial cells, the cells lining the bile ducts, they can modify the bile, and they will do so primarily by adding a watery solution of sodium and bicarbonates. So these guys out here, they can kind of water down the bile before it gets to the gallbladder. Now, when we take a look at bile acid synthesis, of course, it's going to start with cholesterol. So hopefully you can realize the first starting step in this reaction, at least for our purpose, is cholesterol. Now, its conversion into a bile acid involves a very special enzyme called cholesterol 7 alpha hydroxylase. So this is going to basically convert that cholesterol into those primary bile acids, which we've talked about before. So cholic acid, ketodeoxycholic acid, both of those are the primary acids. Of course, after they go through their first pass and they go into the intestines, these primary bile acids can then be metabolized by the bacterial colon, or the bacterial enzymes in the colon, into secondary bile acids. This would include things like deoxycholic acid, ursodeoxycholic acid, and ketodeoxycholic acid. So going from the primary to the secondary in the colon. Now, do remember that each of these bile acids can then, of course, be conjugated with either glycine or taurine to become a bile salt. Bile acids, if you guys recall, are water insoluble, whereas the bile salts are water soluble. So now they can be actually dissolved in the water. All right, guys. So now that we recall a little bit about bile salt synthesis, other things are also going to be taken up through the hepatocytes and continued with the bile. So do you remember that hepatocytes are metabolizing both endogenous and exogenous substances? And these substances move through a series of steps into the hepatocyte and then into the bile canaliculi. So here we have some hepatocytes here, and you can see that we have the sinusoids on the side. Here's our space of D's. And then where the hepatocytes join together, we have the bile canaculus. So the first thing you'll notice is that the hepatocytes are going to import things across from the blood and the sinusoid through the basolateral membrane. So they're going to come out through those fenestrated capillaries here into a space of D's and then into the hepatocyte itself. Once that they come out here, then the hepatocytes will take up the material. They will modify it. They will often either degrade the material or they might conjugate it as well before finally excreting it into the bile canaliculi here, when it can either then be released into the bile itself or modified by the ductual cells. So we'll talk about how that can happen later on as we move forward. Now, of course, to transport these mechanisms, we will be relying on our sodium gradient. So all along the basolateral membrane, we have these sodium-potassium pumps. So here's a sodium-potassium pump here. That's going to provide us the energy in that sodium concentration gradient to drive the movement of several other things. So, for example, the sodium-potassium pumps maintaining that low sodium concentration inside. It's going to be able to use that concentration and pump out protons. So by pumping out protons, here we have a sodium proton exchanger that can actually make this inner area where the bile is going to be a little bit alkaline. And the alkaline bile will help dissolve the calcium salts, the cholesterol, so they don't necessarily precipitate out as cholesterol or bile salts. We also have the sodium bicarbonate co-transporter. And so as the sodium is going out, it can take with it a bicarbonate ion, also helping to increase the alkaline fluid. So I'm sorry, it's taking the sodium in rather, helping to bring in these bicarbonates as well. Amino acids can also be taken up through these sodium amino acid co-transporters. So here we have a sodium amino acid co-transporter that can pull in those amino acids from the space of D's as well. And then we also have our sodium bile transporter. So all of these things are driven, of course, by that sodium concentration gradient, which is maintained by the sodium potassium pump. In addition, there are also basolateral calcium pumps that help to maintain a low calcium concentration inside the cell. So calcium salts are one of those other things that can precipitate out to form pigment salts, which we'll get to later on. And so these calcium pumps help to prevent the formation of those little guys. Of course, there are other bile constituents, and you'll see some of these things are actively secreted into the bile. So, for example, bile acids, phosphatidylcholine, conjugated bilirubin, and xenobiotics are all actively transported into this bile canaliculi here. And these tight junctions will help to make sure that they stay in this area and are not diffusing away. There are other things, though, that can passively follow these structures. So, like I said, the tightness is an intermediate tightness, which means it allows some smaller things through so that we can see water, glucose, calcium, glutathione or thione, which is an important polypeptide for detoxification. That's going to get pulled through as well, and along with amino acids and urea. So just a little bit about some of the other things that we will find in the bile as it's being formed by these hepatocytes. Now, you'll also notice, of course, do remember that a lot of these biles will get reabsorbed, so they'll be secreted out into the small intestine, and as they go through to the distal ileum and into the colon, they're going to actively be taken up in that ileum area, and there are special transporters, which they call apical sodium-dependent bile salt co-transporters. And that's just keeping in mind that we're actively pulling in these bile salts, or I'm sorry, these bile acids from that distal ileum and from that colon. Now, it's important also to remember that not all of these bile acids will be taken up. And in fact, a lot of these guys will make it into the intestine and they will be deconjugated. So those bacterial enzymes in the colon will basically deconjugate the bile acids that do not get actively taken up. And from there, they can actually be passively reabsorbed along the colon epithelium. So once they're deconjugated, they become neutral. They become water insoluble again. And from there, they can just be passively be reabsorbed back up. So you're going to have both an active uptake of these bile acids along with a passive uptake of these unconjugated bile acids, or deconjugated rather. Now, out of all of that, about 10% will escape and they will go into the feces here. So we will have a little bit of fecal loss, which is resynthesized or replenished through hepatic synthesis. So this is just showing us how the hepatocytes can take up bile acids and recycle them and resynthesize them. So wherever we see the Ba, that's a bile acid. And then here's a bile acid that's neutral. And then when it becomes charged, it will become a bile salt. So keep in mind, most bile acids are water insoluble, so they can freely cross through these membranes. And they are often conjugated. And then usually bound, I'm sorry, not conjugated, but bound to albumin as a carrier protein to help make them a little more soluble. Not soluble, but bound to the albumin, they can be transported in the plasma. Of course, the bile salts, when they lose that proton, they become charged and they'll become a bile salt. And that's going to be more water soluble. Now, both of these guys, the bile acids and the bile salts, do get conjugated. So you're going to have that conjugation step with both the bile acids and the bile salts as well as they're going through these hepatocytes. Now, this is our sodium taurocholate. That's just our active transporter, if you would. It's just another name for it. Co-transporting polypeptide. That's going to be pulling these bile salts, transporting them across the cell. So 50% conjugated bile acids, they're taken up through a secondary active transport. That was our active transport here. And do remember that the other 50% will be taken up. They are unconjugated bile acids. And since they're unconjugated, they can be taken up by non-ionic or passive diffusion, just meaning that they're neutral. So I had a few keys there. Must have been in my animations there. So I can tell you what the Y's and the X's are. Y's and Z's. Glycine or taurine. The Z, so that'll be the conjugated here, and then the sulfate or glucouronate for our Y, which we can see down here. Now, also keep in mind, of course, cholesterol, one of the major functions of the liver is to excrete cholesterol and to get rid of extra cholesterol. And there's two ways it'll do this. It'll either get rid of cholesterol in its native form, which it does through 2/3 of the cholesterol, or it will convert it into the bile acid and then excrete the bile acid, and that's 1/3. And the reason I mention this is because a lot of the treatments that we look at trying to treat hypercholesterolemia will try to reduce the amount of intrahepatic circulation so that any cholesterol gets converted into a bile acid hopefully will spill over into the fecal matter and not be reabsorbed. Of course, you can do special medications to do something like that, or just brand out cereal, a very common way to try to lower cholesterol. As we look into the bile ductules, so moving away from our hepatocytes, now we're going into the bile ductules, are specialized cells called cholangiocytes or cholangiocytes. These are the cells that line the biliary epithelia. And they're modified, they're very special here to try to reclaim a lot of those things that are in the bile that we want to keep. So these would be things like glucose, amino acids. So we can see on our apical surface, here's the lumen in the bile duct. So this is what the bile would be, just excreted. We have a special sodium glucose co-transporter that can once again pull in the sodium here, and it's going to bring in with it a glucose. Now, once the glucose is in the cell, it can leave the cell through a GLUT1 transporter on the back end. So that's just going to be able to come right across and reabsorb, taken right out of the cell. Another important component is this tripeptide. It's called glutathione. And like I mentioned, the glutathione is a very important polypeptide in the detoxification step that you will see involved in both endogenous and exogenous substances. And so what we'll see here is that this tripeptide, this glutathione, gets broken down. We have a special GGT enzyme on the surface of the cell here. It gets broken down into these amino acids, and then these amino acids can simply be reabsorbed by these cholangiocytes. Also keep in mind we have this chloride bicarbonate exchanger. So here we have a chloride exchanger, and that's going to pump more bicarbonate, not really pump, but exchange more bicarbonate into the lumen. And that's going to make it alkaline once again, reducing the risk of precipitation of the calcium. One thing you will notice is that when we get to this part of the biliary system, these cells, these cholangiocytes, they're actually being stimulated by this secretin or the secretin hormone, and that's going to stimulate the release of a bicarbonate and watery type of fluid, very similar to what we saw in the pancreas. So not much different in that aspect. Excuse me. All right, so as we're getting into the gallbladder, remember guys, the gallbladder concentrates the bile. We have the sodium hydrogen exchange that can reabsorb the sodium, and it's going to pull with it chloride and water. As for the bile salts and the bile acids themselves, they're too big. They won't be able to get pulled in, so they're going to be left here in that lumen, and they're not going to be reabsorbed. So by removing the sodium, by removing the chloride and the water, leaving the bile acids in the lumen, that's going to allow us to concentrate the bile in the gallbladder. Of course, we do want to keep in mind when we're thinking about bile formation, gallstones is a big step. And here we have a nice biliary tree. And what we want to think about is how they're actually formed. Now, there are a few different types of gallstones, if you would. We have what we call cholesterol gallstones, which they call cholestasis. It's about 6% of your total overall stones. That's composed primarily of cholesterol. You can also have pigment stones. Pigment stones are composed of calcium salts. It could be calcium phosphate, calcium bicarbonate. A number of those calcium salts will be pigment stones. Most gallstones, however, are mixed. They're composed of cholesterol along with the different calcium salts. So calcium phosphates, carbonates, and palmitates. There are a lot of different factors that go into the formation of gallstones. Of course, diet being a big one, but we also think of cholesterol supersaturation, especially during fasting. So what that means is if you go long periods of time without eating meals, we see the link here between that and the formation of gallstones, where the cholesterol becomes supersaturated in that gallbladder. Also, age and sex play a role. So we'll see that middle-aged women tend to have more gallstones than men. And genetics. There's actually specific genetic polymorphisms that actually contribute to the formation of gallstones. And here is one where we see a polymorphism in the hepatic cholesterol transporter, where we can see this is more likely to occur in some individuals than others. We do also notice that oral contraceptives have a slight role in the formation of gallstones. That's just one of the cons, but the benefits that we see definitely can probably far outweigh those, especially with some of the preventative effects of cancers and whatnot. But there we have just a few factors that would go into playing the role of formation of gallstones. Now, when the bile cannot be released from the biliary tree, this is what we call cholestasis. Cholestasis simply means the bile stops flowing like it should. So it's not the same thing as a gallstone, or it could be a gallstone, but it's just the blockage. And there are several things that can cause this. So a couple things to keep in mind. First of all, the negative effects. What happens here is that this is going to cause the regurgitation of bile components back into systemic circulation. So as that builds up, you could get that portal hypertension, and then the bile can start to cause things like jaundice from the bilirubin in the bile, pruritus, itching sensation, if you would. Now, this will also damage the hepatocytes. It'll damage those tight junctions and chemically damage the cells themselves. And it's also going to slow down and impair your lipid digestion and absorption. Depending on where the effect is at, what's causing the cholestasis, it could either be extrahepatic, which just means it's happening outside the biliary tree. This could be something like a chronic or acute liver disease. Maybe something's inflamed and is blocking the flow at the hepatocytes. Or it could be within the biliary tree. In that case, we would call it intrahepatic obstruction of the bile ducts. So both of those could lead to a cholestasis. So this just kind of shows us what's going on, some of the consequences of cholestasis. So let's say you have an obstruction to the outflow of bile. Maybe there are some stones that are blocking the outflow here at our hepatopancreatic ampulla or sphincter. And now you can start to see that we have this backing up, if you would, of the bile. So that's going to increase the pressure within that biliary tree, and that's going to also cause the loss of hepatocyte polarity, and they're going to lose those abilities to function properly to take in certain molecules. That's also going to disrupt the tight junctions between the cells, and it'll ultimately result in hepatocyte necrosis, killing the cells off. Now, this, if severe enough, can then lead to a rupture of the biliary canal. So as this canal starts to rupture, that's then going to cause this reflux back into those sinusoids and ultimately either back into the venous system, which will result in cholangilovenous, or it could go back into the lymphatic system, which would be cholangilolymphatic reflux. So showing us a couple of those areas where we can have reflux of the bile if it's obstructed. So just to give you guys a few symptoms of things that would happen with systematic effects of bile reflux, we would have that itching due to the bile salts. Also, poor wound healing. So you'll see that all these wounds may not heal properly. And interestingly enough, bile reflux or bile salts actually have an effect on cardiac function, where they actually suppress the SA node. So you might see a slowing of the heart. You get this bradycardia. You might also see a slowing contractility or decreased contractility, even decreased peripheral resistance. So you're going to start to see this kind of heart feeling thing, if you would. And what you'll notice then is that if it's severe enough, as the cardiac functions go down, that could then secondarily cause a renal failure as well. So just to give us an idea of what's going on when these bile acids and these bile salts start to back up into our systemic circulation. With that said, guys, let's now take a look at bilirubin. And do remember, guys, bilirubin is an important part of bile, but it is not bile. And so the physiology and the pathologies that occur with bilirubin are going to be a little bit different. And bilirubin, of course, is a byproduct of red blood cell breakdown. So if we have hemoglobin here, which is this molecule of heme in the center surrounded by this polypeptide, that's a globin molecule, you will notice this hemoglobin gets broken down. We have the molecule of heme that contains the iron along with these carbon molecules, and then the globin. The globin part will be broken down into its constituent amino acids, which then can be modified and reabsorbed if need be. Whereas the heme, that will then be broken down into iron. The iron gets released, and then the bilirubin gets released and then broken down ultimately into bile, which can then be released into the gallbladder. So what we'll do is follow these molecules down, this molecule of heme, and talk about the major steps that are going on as it's being broken down. So the reason why this is important is that bilirubin can be potentially toxic. If it's unconjugated, it can cross the blood-brain barrier, which can then lead to cell death, neuronal cell death, followed by brain dysfunction. If left untreated, it can actually be fatal. So we do want to make sure we keep our bilirubin levels low. And this just follows the heme metabolism. So once we've broken apart the red blood cell, there's our molecule of heme with the iron in the middle. And here we see the iron getting released over here. And then we're going to have our biliverdin over here getting released. And we can see the biliverdin getting broken down through a series of steps into bilirubin. And notice microbial enzymes will then break it down into urobilinogen, which if it goes into the kidneys, passes through the kidneys, it can then be converted into urobilin. So we'll follow that. There's a couple of ways, a couple different pathways that we'll actually take, which we can follow. So getting rid of the bilirubin then is a multi-step process. There are a few steps going on here. And it's going to start with those cells of the reticuloendothelial system, or the RES system. These will be primarily your Kupffer cells and the macrophages in the spleen. And what they'll do is they'll release the iron from the heme. And so there's a special enzyme in here, heme oxidase, that can release that iron. And that's going to then give us our biliverdin. So here we have this kind of green pigment biliverdin from the release of the heme, or the iron from the heme. Notice here's the iron that has just been released. From there, the biliverdin can then be reduced into a bilirubin. And so we're going to go from a green pigment structure to a yellow pigment structure as the biliverdin gets converted into bilirubin. Now, bilirubin itself is water insoluble, so it will have to be bound to a carrier protein. In this case, it's albumin. And so now we have this bilirubin albumin complex that can carry the bilirubin out through the bloodstream. Ultimately, this bilirubin will be taken up by the hepatocytes. Active transport will pull those right off the albumin, taking them into the cell where they can either be conjugated or modified. So what we'll see is that as these guys are taken up to the hepatocytes, let's say we have our bilirubin here. Here's our bilirubin albumin complex. The bilirubin is getting taken up. We then have a special enzyme in here called UDP, glucouronyl transferase, that can then conjugate the bilirubin with glucouronic acid, and that's going to make it water soluble. Now, not all of the bilirubin will get conjugated. We'll talk about how that works later on, but some of this conjugated bilirubin will then be released into the kidneys or filtered through the kidneys, where it then can be converted into urobilinogen and then into urobilin, where then we'll give urine that pigment color, the yellow pigment. Now, some of this conjugated bilirubin will make its way through the intestines, where it can then be converted into urobilinogen here. And then from here, the intestinal bacteria will convert it into urobilin or sterobilin. And these pigments are what give the feces their kind of brownish color. So you're going to see whether we're dealing with sterocobilin and urobilin. That's going to give the pigment in the feces. Whereas the urobilin, also known as urochrome, would give that pigment in the urine. So this is just following the same pathway. So here we see our bilirubin albumin complex. You'll notice the bilirubin being taken up. Some of this will be unconjugated. If it's unconjugated, it may or may not go through a carrier protein. I have question marks there because we don't really know, but we think it can easily just diffuse across the cell. Over here, conjugated bilirubin can actively be taken up, and we can then transport it into the bile, conjugate it, and then take it into the bile. Notice that the bilirubin glucouronide conjugate here then can be deconjugated into bilirubin, which can then be broken down into urobilinogen and then either excreted into the small intestine through converted into sterocobilin and excreted into the feces, or if it's conjugated, it can go out here into the urine and where it's released as that urobilin pigment. So that's going to give that urine its yellow color. All right, I thought this was just interesting. The same concept here, breaking down the formation of bilirubin from heme. And the thing that you'll notice, an interesting case of this, is with the black eye. So if somebody punches you, they give you a nice black eye. Well, the original blackness is coming from the release of all that heme. And that's going to start as a black color. But as you notice, as time goes on, we're going to have the oxidation of this heme, and it's going to degrade into biliverdin. And biliverdin itself is going to be a green color. So you'll get that kind of green pigmentation a couple of days later. And then finally, through the action of biliverdin reductase, this special enzyme here, that will then be converted into bilirubin, which will be that nice yellow color. So going from black to green to yellow of the black eye is that kind of breakdown of the heme occurring right beneath the skin. All right, so like I mentioned, not all of the bilirubin will get conjugated. There is both conjugated and unconjugated bilirubin. Excuse me. And so what we can see here are some differences between the two. Typically, you'll see the unconjugated bilirubin present in the plasma. And if it is present, since it's water insoluble, you will find it bound to albumin. Conjugated bilirubin, on the other hand, it's normally in the bile, not the plasma. So once it gets conjugated, it can be excreted into the bile, and it will be conjugated to that glucouronic acid. Unconjugated bilirubin also has a high molecular weight, so it will not be passed into the kidneys. So this will not be processed and released into the urine, whereas the conjugated bilirubin has a smaller molecular weight, and if it is present, can be filtered through the kidneys and converted into that urochrome to make the yellow coloration of the urine. Also, of course, we should know that unconjugated bilirubin is nonpolar, so it can easily cross the cell membrane, and that can even cross the blood-brain barrier, causing a potential brain damage in neonates or newborns. Whereas polar or conjugated bilirubin is polar, water soluble, and we do not have to worry so much about it crossing the blood-brain barrier. So just to give you guys a couple of those differences here. So guys, of course, we want to think about jaundice. This scientific name for it is also called icterus. But we don't want to wait for icterus. We don't want to wait for jaundice. We want to measure the bilirubin. So simple dipstick can do this. Take a look for bilirubin area to measure your bilirubin in the plasma before it becomes physically apparent. And when we talk about jaundice, this, of course, is referring to excess bilirubin in the extracellular fluid. So you're going to get these bilirubin spilling over into the extracellular fluid. It can either be free bilirubin, unconjugated if you like, or the conjugated bilirubin. It all depends on the cause of the jaundice. Now notice under normal concentrations, the bilirubin concentration is about 0.5 milligrams per deciliter or deciliter. And now what we'll see is that with jaundice, when you start to see it, it usually goes to about 1.5 to about 3 milligrams. And it can even get all the way up to 40. So that's pretty darn jaundiced. And then we can see the physical appearance here with the pigmentation of the skin and the sclera. Now, there are several different causes of jaundice, but we can break them down into 3 basic categories. We can have prehepatic, hepatic, or posthepatic. The first one we'll look at is called prehepatic, also known as hemolytic. As the name implies, this is occurring with excess red blood cell breakdown. And so as the red blood cells are being destroyed or being broken down, they're releasing that bilirubin into the plasma, into the blood. And this will overwhelm the liver's ability to conjugate the bile. So what you'll see here with hemolytic jaundice is that most of this will be in the unconjugated form or unconjugated hyperbilirubinemia, because the liver cannot keep up with the excess red blood cell breakdown. You'll often see this in anything that would destroy red blood cells, like transfusion reactions, malaria, sickle cell anemia, thalassemia as well. And you'll also see this in newborns, right? So newborns, there's a couple of reasons why we see this. First of all, we have an increased red blood cell turnover, but we also have immature conjugation pathways. The newborn doesn't have the enzyme UDP glucuronidase transferase fully formed yet. That's not really starting to be synthesized till after birth. And so you'll see that we'll have a little bit of buildup because we can't quite conjugate the bilirubin. So what's the treatment? Well, basically just stick your baby in a windowsill, right? You get that nice phototherapy. Put it outside in the sunlight for a little bit. And that'll help decompose or break down that excess bilirubin. Excuse me. So some of the things that you'll notice for hemolytic jaundice, you're going to have this kind of this pale skin. Also, because you're going to have these unconjugated bilirubins, you're going to get this normal or dark stools. So a lot of that will be released into the feces. And the urine itself will be a dark color because you're going to have that increased urobilin, if you would. So there's a little bit of hemolytic anemia. You could also have hepatocellular anemia or hepatic. In this case, not anemia, jaundice, my bad. With hepatocellular jaundice, this is due to hepatic dysfunction. So the cells are not working properly. So when the liver cells are so damaged that they cannot transport the conjugated bilirubin into the biliary system, that's going to impair their ability, causing this type of jaundice. So you'll see this with, of course, cirrhosis, drugs, liver cancer, and hepatitis. Anything here that's going to damage the liver. There are some other examples. There's a congenital disease called Gilbert syndrome. It's relatively benign, but it is a mild genetic disorder where the liver does not process the bilirubin properly. In this type of jaundice, you'll see both a rise in conjugated and unconjugated bilirubin increasing in the plasma. So if you see both conjugated and unconjugated, that might be a sign that something is not functioning properly in the liver. The liver cells themselves might be damaged. A third type is a posthepatic, also called the obstructive jaundice. And as the name implies, this is due to some type of obstruction, either within the biliary tree or within the liver itself. But the point is the bilirubin cannot be drained. And so the bilirubin that's not excreted will have been conjugated by the liver, And so you're going to see a rise in primarily conjugated hyperbilirubinemia. A few things that can do this: gallstones, inflammation of the liver, scar tissue, tumors that might block the flow of bile. The tumor does not have to be in the liver. You could have, for example, a pancreatic cancer or abdominal mass, and that can still block the flow of the bile, causing this obstructive type of jaundice. What you'll notice here is that you're going to have lipids in the stool, steatorrhea, along with weight loss. This will result in dark urine because you have all this conjugated bilirubin building up. And because it's not able to make it into the bile and release into the intestines, the feces will actually take on a kind of a clay color because they will not have that sterocobalamin that gives them their normal brown color. So you'll actually see this kind of a clear clay colored stool with obstructive jaundice. So here's one of those nice little illustrations that shows us the different type: prehepatic, hepatic, or post-hepatic jaundice, kind of giving us an outline of their causes and their manifestations. With that said, guys, now let's turn our attention to some of the metabolic functions of the liver. So the liver has a lot of different metabolic functions. Carbohydrates, proteins, lipids. We'll take a look at all of these. In terms of carbohydrate metabolism, of course, one of the main functions here is to store and synthesize and store glycogen. So glycogen, if you guys remember, is a polysaccharide, but a polysaccharide, if you would, where glucose is converted into this glycogen in the storage form of energy. So when we have excess glucose in the plasma, let's say after a nice meal, maybe have a few yeast donuts and some orange juice, glucose levels go up. We have a bunch of extra glucose. That'll get transported into the liver cells, and then the liver cells can take this glucose and then convert it into glycogen up here. And then that glycogen can be stored for in between meals. That way, after a couple hours, when your glucose levels start to go down, we can then release the glycogen, break it down for glucose after a meal. So once you're in between meals, we have glycogenolysis. That is the breakdown of the glycogen. So this glycogen that was being stored will then get broken down through a series of steps and then released as the glucose, elevating the blood sugar levels again, keeping them nice and constant. Also, if you guys remember, when we take up our monosaccharides, we'll take up three sugars: lactose, fructose, and glucose. But the galactose and the fructose, they will be taken to the liver and get converted into that glucose molecule there. So another important function of the liver. And of course, it can also carry out gluconeogenesis. That's making glucose out of non-carbohydrates. So you can take, for example, the glycerol, or maybe you can take the amino acids and convert them into glucose. That's one of the major functions of the liver here, gluconeogenesis. So there's its major role in carbohydrate metabolism. So this just reminds us of what's going on. You want to keep your blood glucose level. So when it starts to get too high, maybe after a meal, elevated blood glucose gets taken to the liver. It will be formed into glycogen, and that's going to pull the blood glucose back down. Then after a couple hours, as your blood glucose starts to fall, well, then in the liver, we're going to have that glycogenolysis. We'll break the glycogen down into glucose, and that's going to release the glucose back into the blood, elevating the blood sugar levels again. Anything that's not used, that's not oxidized, will then be metabolized to fat. So in terms of protein metabolism, the liver does a lot with proteins. First of all, it's going to be involved in deamination, taking the nitrogen off the amino acids. Also, it can synthesize non-essential amino acids as well. It's also involved in the formation of urea to remove the ammonia, and it's also involved in the formation of plasma proteins. In fact, most plasma proteins, aside from gamma globulins, which are produced in your lymphatics, most of these guys will be produced in the liver. And also it's involved in the interconversion of various amino acids, where it can convert one amino acid into a different kind. And we'll talk about how that's done here in a few minutes as well. So first of all, let's take a look at deamination. Deamination is the removal of this amine group here from the amino acid. And this is required before the amino acids can be used for energy or for other purposes. So what'll happen is that we have this deamination, and that'll convert this into ammonia, which can then enter into the urea cycle. As for the remaining carbon skeleton, these carbons, these oxygens, these R groups, they can either then be oxidized for energy, converted into glucose, acetyl-CoA, ketone bodies. They can be used in many other carbon reactions, if you would. And this does occur in some other tissues like the kidney, but the big site for deamination of your amino acids is our good friend, the liver. We will also have transamination of amino acids. Transamination of amino acids is where we take the amine group from one amino acid and use it to synthesize a different one that we might need. So this is how we synthesize our non-essential amino acids. And this is important because what happens is we have these keto acids that have the same chemical composition as the amino acid. The only difference here is this amine group here and this oxygen group here. And so what you'll see is by swapping these guys out, pulling this amine group over here and the double bond oxygen, the keto oxygen over here, we can actually synthesize a brand new amino acid. So to show you how this would be done, we have a special enzyme. To give you an example, alanine transaminase, and this is going to transfer an amino group from alanine to alpha ketoglutarate. So there's our keto group here. Here's our amino acid here. And by transferring the amino acid over here, we can then form glutamate, and then we'll also have the oxygen come over here to make this pyruvate. So this is catalyzed. We have this special alanine transaminase. That's a type of amino transferase enzyme that can transfer that amino acid to form a new amino acid. Of course, as we're producing deaminating and we're forming this ammonia, one of the other things that the liver does is removes the ammonia. And this is going to be done through the urea cycle. So here we can have either ammonia or in this case ammonium that gets removed. And what you'll see here is that this ammonium, this gets very toxic in the plasma. So we have to get rid of it. We have to neutralize it. And this is done through the urea cycle. So what the liver does is it'll take an amino group here and it'll combine it with an amino group from this aspartate. And as these guys come together, those amino groups will then be converted into urea. And that's relatively mild compared to having ammonia in the plasma. So other animals like fish, they have other ways to excrete ammonia. But as for us mammals, we will be converting it into urea so it's non-toxic. Of course, we want to be able to handle the urea. So what we can see is that the ammonia is a really small neutral molecule that is readily reabsorbed. And so we need to be able to handle it in a safe way. And what you'll see is that a lot of this ammonia and all of this urea, in fact, will get reabsorbed through what we call this portal circulation. So here we have some ammonia coming back to the liver, about 85% of it, that will get recycled, reabsorbed, then converted into urea, which can then enter our systemic circuit. And so from there, some systemic circuit, it can either go to the kidneys, where some of this urea will be excreted as urine, and then some of this will actually go into the intestines, into the colon, and it can either then be reabsorbed again or be excreted as the ammonium ion. The thing about the ammonia is that it's readily reabsorbed, whereas if we protonate, if we add the hydrogen and convert it to ammonium, this cannot be reabsorbed. So that will be stuck out here in the colon, and then it can be excreted into the feces. Excuse me, guys. All right. So about 50% of the ammonia that we're looking at is actually produced in the colon by different bacteria. And they have these enzymes, ureases, and that will actually be what's producing a lot of the ammonia. So like I mentioned before, some of this is converted to ammonium, which cannot be reabsorbed because it is a polar molecule here, and that will be excreted into the stool. The rest of the ammonia is neutral, and it will readily be reabsorbed, transported to the liver by portal circulation. So we saw back here where we had about 75% of that, 85% of that urea, or ammonia rather, coming back here through that portal circulation. You also notice that about 40% of the ammonia is being formed from the kidneys themselves, and then we have another 10% coming from the deamination of amino acids. Our next stop would be lipid metabolism. So when we're looking at lipid metabolism, we'll take a look at both the anabolic and the catabolic reactions. As for the anabolic reactions, the liver is responsible for the formation of cholesterol and fatty acids and can make these de novo, so it makes them out of the basic building blocks. And it can also synthesize fats from different proteins and carbohydrates. When we look at the catabolism, we'll also look at the oxidation, the breakdown of the fatty acids, and that's going to supply the body with a source of energy, if you would. So let's start with the formation of cholesterol and fatty acids de novo. And what you'll see here is that will occur in the liver and the other tissues, but the liver is the big place. And we're going to start with this special molecule here called acetyl-CoA. So if you guys remember your oxidative phosphorylation, we always started with acetyl-CoA. That was the common pathway. It's even the common pathway here for lipid synthesis. And through a series of steps, and we don't need to worry about all these steps, but it will be converted ultimately either into fatty acids or into cholesterol. So you're going to see the synthesis of cholesterol here. Now, I mentioned this because there's a group of statins here, and these statins are acting on these enzymes to help prevent that conversion of the acetyl-CoA into the cholesterol. So that's one way to kind of reduce our plasma cholesterol, is using these statins to help inhibit this HMG coenzyme A reductase. All right, so we also want to take a look at the synthesis of fats from carbohydrates and proteins. So these are other ways that we can make fats. And we, of course, once again, we're going to start from acetyl-CoA. And so what we'll have is the acetyl-CoA being metabolized from the carbon skeletons of our proteins or from our carbohydrates. Like I mentioned before, that's the same molecule we saw in the oxidative phosphorylation cycle, the citric acid cycle, if you would. And so it can also enter another pathway, lipogenesis. And this lipogenesis pathway then can use those acetyl-CoA molecules to make new fats. The catabolic functions of the liver is the breaking down of the fatty acids through what we call beta oxidation. So this beta oxidation will break apart these carbons, and that's going to release the energy, giving us another energy source that the liver can supply. Another thing to think about is the liver's role in controlling cholesterol metabolism. So when we think about cholesterol metabolism, we want to think about how the liver takes up cholesterol, how it processes it, how it forms it. And what we can see here is that it's actually going through these different cycles, through these different pathways. We have an endogenous pathway over here, what's going to occur within the liver and with other tissues. And we also have an exogenous pathway here that's going to be involving the gut. And so in the exogenous pathway, the liver is taking up dietary cholesterol as those remnant chylomicrons. And as it takes them up, it will then export them and their metabolites into the bile. So going from the liver or from the plasma into the liver, we take up these chylomicrons, triglycerides, cholesterols will be formed, and then the cholesterol then can be secreted into the bile acid. And then some of that will be excreted from there. Some of that will, of course, be recycled through that enterohepatic circulation. And some of it will be lost through our feces. As for the endogenous loop, the liver is going to export cholesterol and other lipids as VLDLs, so very low density lipoproteins, and it will also take them up from the blood as LDLs, low density lipoproteins. So we're going to have this cycle here between the very low density lipoproteins and the low density lipoproteins. And I'll come back to these guys here in a second. But what we'll see here is that when we start to make and remove cholesterol, well, the liver, first of all, it obtains cholesterol from three major sources. So first, we see that you're going to have the dietary intake of cholesterol, those chylomicrons. They can be taken up by the liver. That's a big source of cholesterol. Not a big source. Well, there's a prominent source. It's an important source. But there's also other sources as well, right? So we saw that the liver can also synthesize cholesterol de novo, so it can make its own cholesterol from its stores. And it can also take up cholesterol in the guise of those low density lipoproteins, those LDLs. As for removing the cholesterol, if you want to get rid of it, well, the liver can export the cholesterol in a couple of different ways. Number one, it can use the cholesterol to make new bile acids and then release the bile acids into the biliary tract. But it can also export the cholesterol to the blood in the form of VLDLs. And of course, when that happens, the cholesterol circulates into the plasma and then can be deposited into other tissues, like your blood vessels, if you would. So it's a good time to mention the different types of lipoproteins. So we talked a little bit about LDLs and VLDLs, and we should understand what they really are and what they really mean. And these are the different types of lipoproteins that are responsible for transporting the lipid components in the blood. So a big guy right here is what we call the VLDLs, very low density lipoproteins. And we call them very low density because they are filled with high triglyceride content. And they have a lesser extent some cholesterol in them and some phospholipids. And it's these VLDLs here that are transporting those triglycerides formed in the liver to other areas like your adipose tissue. So they can deposit that triglycerides, those fats, into your adipose. Now, if you remove some of the triglycerides and get rid of the tissue, maybe into the adipose, then we form something called the intermediate density lipoproteins, or IDLs. These are very similar to your VLDLs, but they're going to have some of those triglycerides removed. And because some of those triglycerides are removed, they will have a higher concentration of cholesterol along with phospholipids. If you remove most triglycerides, well, then we get low density lipoproteins, LDLs. So LDLs are essentially derived from these IDLs by removing all of the triglycerides. If you get rid of all the triglycerides, maybe you deposit them in the adipose tissue, that's going to leave behind cholesterol and phospholipids, and they're going to be especially in high concentration with these LDLs. So you can imagine why we monitor a person's LDLs levels. And last but not least, we have our high density lipoproteins, HDLs. These will have a higher concentration of protein in them, making them a higher density, but they're going to be much smaller concentrations of cholesterol and phospholipids. Now, some of the evidence is recently kind of up in the air, but it turns out there's some evidence that it may help absorb cholesterol crystals that are already deposited in the arterial walls. So, good job for the HDLs. So there are, of course, several factors that will affect plasma cholesterol concentration. More cholesterol we ingest each day, that can increase the plasma. But there are negative feedback mechanisms that will prevent the cholesterol from getting too high in the plasma. So what you'll see here is that rising cholesterol will actually inhibit most essential enzyme activities that are needed for cholesterol synthesis. So when we start taking in our own cholesterol, then the liver will stop producing its de novo cholesterol. Of course, another factor is a highly saturated fat diet. That will increase cholesterol 15 to 25%. So definitely having to watch the saturated fats because they can have a pretty big impact on your cholesterol levels. Ingestion of fats containing highly unsaturated fatty acids can actually depress the cholesterol levels by a slight amount. So even a slight or moderate amount of these taking in some of these unsaturated fatty acids can actually have a lowering effect of the cholesterol, which is why they typically say if you're comparing saturated versus unsaturated, this has a slight beneficial effect to it. Also, other things that will do it, lack of insulin, so think diabetes mellitus or thyroid hormone, that will also increase those cholesterol levels, kicking those up a notch. And then we also, as we saw, hyperlipidemia or hypocholesterolemia rather, some genetic disorders can affect cholesterol metabolism as well. So there are, of course, genetic components. Excuse me, guys. And this is just kind of showing us a pathway of how the liver is handling these different lipids. And so when we talk about those triglycerides that are in the adipose tissue, they can then be released as free fatty acids, and these free fatty acids can be taken up and then converted into some of those, incorporated into those bile acids. Bile acids can then either be ingested or released into the liver, and we can also add some more of those fats from our diets as well. These guys transported in the chylomicrons can either be deposited, once again, as free fatty acids, get converted back into triglycerides, or they can be transported by those LPLs and transported back into the liver. So kind of giving us a little pathway of how these liver, the adipose tissue, and the peripheral tissue can deposit some of these lipids, these free fatty acids, in the triglycerides, and then also taken up into the liver. Of course, it reminds me, it's always good to keep in mind with cholesterol, atherosclerosis. And of course, we see atherosclerosis is actually this kind of inflammatory response where we start to have these lipoprotein particles here, these lipid droplets, if you would, get released. Here we have, for example, a monocyte. Monocytes, of course, are your white blood cells starting to leave the bloodstream into the plasma, getting converted into a macrophage. And these called these macrophage foam cells. And what can happen then is that these foam cells can start to release these little lipid droplets that can then stimulate and kind of form these little areas of plaque. Do you notice the plaque's not on the inside of the arterial wall? Here is our endothelium. Rather, it is embedded behind here into that tunica intima, that inner tunic layer. And here we can start to see that small plaque starting to form into a larger plaque. And then if it ruptures, it can then create this kind of thrombus, if you would. So just a little bit about the cholesterol's role in the formation of atherosclerosis and the formation of a thrombus. Of course, we want to think about some of those factors that affect atherosclerosis, such as physical inactivity, obesity, diabetes mellitus, hypertension, hyperlipidemia, cigarette smoking, and men will typically have this more susceptible than women. Now, an interesting side note is the effects here, they are not additive, but they are rather multiplicative, where they can exponentially increase the factors. So, for example, let's say we have hypertension in our patient. Well, that will increase the risk of coronary artery disease by at least twofold. Diabetes mellitus, well, that will also add another twofold. But these two won't add together. If you have both hypertension and diabetes mellitus, that will actually increase the risk of cardiovascular disease by eightfold. So a much, much bigger jump there, having both of these together. And of course, if your patient has hypertension, diabetes mellitus, and hyperlipidemia, well, now we have a 20-fold increase. So you can see how the numbers jump way, way up as we start adding on these different risk factors for each individual. Of course, you want to consider prevention, healthy weight, staying physically active, preventing hypertension. So if you can't do it through diet and exercise, hypertensive drugs definitely are a good way to do it. Controlling blood pressure, controlling blood glucose, especially with diabetes. If you have diabetes, definitely keep an eye on blood glucose and avoid smoking. Couple words about iron storage. So, of course, the liver plays a major role in the storage of iron, and the form of iron that's being stored in the liver is ferritin. So we've looked at this a little bit before with absorption and secretion. But what you'll see is that the iron from the transferrin, that's where it's bound to in the blood. It's loosely bound in the blood to this transferrin. It gets transferred to the liver where it combines with this protein called apoferritin. And when it binds with the apoferritin, that's going to form this ferritin here, which is the storage form of iron. Now, this apoferritin-ferritin complex, this apoferritin and the ferritin system, where we have these two working together, will act as kind of an iron buffer, where if we have too much iron, we can deposit it into the liver. Too little, we can then release it from the liver. So when your blood iron level is high, let's say we have a bunch of extra iron in the blood, well, it's bound to this transferrin molecule here, and it's going to be transported to the liver, and that iron then can be released. And here we see this free iron, the Fe3, this ferric, getting reduced into the Fe2. That will then be bound to our apoferritin to form our ferritin, and this will then be stored in the liver. When blood iron is getting low, then, well, the ferritin here can then release the iron. And so we see the iron getting released from the ferritin, forming that iron and the apoferritin. Iron getting transported out into the blood, getting converted to iron 3, and then that iron will then be bound to the transferrin, where it can then be transferred through the blood plasma. So we can see we can have this increase and decrease in the iron as one of the liver's major roles. This is just showing us how excess iron is deposited in the other tissues, especially the liver hepatocytes, and less so into the RES system, the reticuloendothelial system of the bone marrow as well. So the liver, bone marrow, a couple of major places that we can store the iron. So when the iron is absorbed from the small intestine, it immediately combines with the beta globulin, and that's that apotransferrin that we were looking at. And excuse me, that's going to form that transferrin, which can then be transported in the plasma. There's our transferrin iron. Here we go into our liver. That'll be our tissue here, where the free iron then gets combined with the apotransferrin to make that ferritin. And now that ferritin can be stored until we need it again. Once we need it again, it can then be released as free iron, converted back to transferrin iron, and then that can be transferred through the blood. Excuse me. Of course, we also want to take a look at the liver's role in detoxification. So when we think about detoxification, guys, I'm sure with pharmacy have probably already talked a little bit about this, but we have this first pass metabolism where everything coming from the portal system will first go through the liver, where it can then detoxify and then release that blood into the vena cava. So liver detoxifies substances originating from the gut or elsewhere in the body, and it will detoxify them through physical methods. Think about your Kupffer cells, as well as through different biochemical reactions, different enzymatic reactions. Metabolites are then secreted into the bile and eliminated through the gastrointestinal tract. So to show you this, let's suppose we're passing our toxins through the liver. As they go through the liver, there are physical methods here through the Kupffer cells that can actively take up the foreign substances, the molecules. And then we also have these biochemical reactions that can enzymatically break down the toxins. Now, as we do, we will go through a couple of phases. There is what we call a phase 1 reaction, followed by a phase 2 reaction. In the phase 1 reaction, we have oxidation and hydroxylation of the chemicals. And this is mediated by a very important enzyme called cytochrome P450. So this guy right here will mediate the oxidation and the hydroxylation of these different biochemicals that are being broken down. After that, we will have a phase 2 reaction. This is esterification of the substance. And basically what we do here is conjugate the substance with glucuronide, sulfate, amino acids, or glutathione. And by conjugating it, that will make it water soluble, which can then be released into the bile as a waste. So that'll help us get rid of some of those foreign substances in detoxification. Of course, the liver also plays a major role in vitamin storage. The vitamins being stored here, vitamin A, vitamin D, and vitamin D or B12. Of course, we always want to think about taking too much vitamins. So if you take vitamin A is one of the big guys that you can actually take too much of, and then we end up with what we call hypervitaminosis A. And that's when we take too much of the vitamin A and it starts to accumulate. So that'll be associated with hepatotoxicity, and that can lead then to portal hypertension, and if severe enough, can ultimately result in a cirrhosis. As for vitamin D and B12, the liver is, of course, storing vitamin D, we've seen here, and B12, and it's also involved in the activation of vitamin D. One of the important things that the liver does is it prevents vitamin D deficiency. So it'll give us a nice storage here for about 3 to 4 months of vitamin D before we start to notice the effects of vitamin D deficiency. As for B12, well, it can store enough B12 here to last us for a good year. So go liver. Last but not least, do a couple of clinical assessment functions of the liver. So I'm going to take a look at some basic liver tests. Some of these will be involving the enzymes that we've looked at. And so a lot of these tests, they will bundle all these tests together, which can look for a few different things. So for example, we'll be looking for bilirubin. You want to check for both the conjugated and the unconjugated form. And that, of course, helps us distinguish whether it's pre-hepatic, hepatic, or post-hepatic type of jaundice. And then we can also talk about whether it's direct or indirect. Direct or indirect are other terms that we use for the conjugated or unconjugated. In addition, we're going to test for a few different enzymes. And so notice that these are a couple of those transferase enzymes that are involved in transferring the amine groups. Aspartate transferaminase, alanine transferaminase. Looking for these will often be elevated with hepatocyte injury. We can also look for our gamma glutamyl transfer peptidase, or transpeptidase, if you would, and you'll see this with damage to the cholangiocytes, so those gallbladder cells. If they get damaged, that can change those values as well. Alkaline phosphatase, lactase dehydrogenase, ALP-LDH, and we also want to look at some basic plasma proteins. Prothrombin time, so for the clotting factors, because the liver is making the clotting factors, if the prothrombin time is extended or if it's delayed or if it's shortened, that might indicate some dysfunction with the clotting factor formation. And of course, albumin being one of those major guys secreted and produced by the liver. So here's a nice little reference range for hepatic function panel. When you're looking at hepatic function panels, we don't need to memorize all the numbers here. Just keep in mind the AST, ALT, GGT, these should all typically be under about 50. If you start going over the high value here, that's definitely not a good sign, indicating some type of hepatocyte damage. Albumin, somewhere between 3 to 5 typically in the plasma. And then you, of course, with total protein, think about between 6 and 8. Bilirubin, as long as it's less than 1, that's the important thing. And alkaline phosphatase under about 135, 136. So just keep in mind, these are some of the common tests that you'll typically be looking for. A lot of these are proteins, enzymes, and things that we've looked at throughout this lecture. So hopefully they will start to look a little more familiar to you as you move forward. And of course, just one last note with some diseases. We've already talked about most disease, so the only one I'll add on here is cirrhosis. And what happens with cirrhosis is that you get fibrous tissue replacing the damaged parenchymal cells. So your hepatocytes get damaged, they get destroyed, they get replaced with this connective tissue. And one of the big things that we'll do, of course, is impede portal blood flow, resulting in things like that portal hypertension. Now, this can be alcoholic or non-alcoholic, but if we think of alcoholic cirrhosis, a lot of times you'll see patients go through a stage of hepatitis first and then through cirrhosis. But you'll also see that a lot of patients, in fact, most patients, have no history of alcoholic hepatitis. They go straight to cirrhosis. Now, with abstinence, a 5-year survival plan, if you can have your patient stay abstinent, look at this, 89% survival rate. But if they continue to consume alcohol to drink while they're trying to recover, look at the recovery plan, the survival. 5-year drops all the way down to 34%. So you can imagine why abstinence is such a big factor here to keep the patient in the 89% group here and not drop them down to that 34% group. And of course, with abstinent patients, if they do maintain abstinence, then liver transplantation is one of the factors. So guys, after all that, I do apologize for this late lecture, but hopefully that'll cover everything for our digestive chapter. So you enjoy the rest of your afternoon, and I look forward to seeing you guys on Tuesday. We'll talk about the endocrine system then. I'll see you back here then.